Okay, thank you very much. Good day, everybody. So let's start with an outline of my talk. I will talk about uncertainty quantification of atmospheric transport and dispersion models. The talk is based on three parts. First, I will give an introduction to atmospheric transport modeling, and then also the ensemble method to quantify uncertainty, which is the main part of my PhD. And then I will show two applications, which can be called the forward problem and the inverse problem. So the forward problem is basically the problem where we have known sources and we try to calculate concentrations at certain locations. And we will show an example where we calculate the xenon concentrations of certain isotopes in Europe. For the inverse problem, we don't know the source, and we will show an application where we investigate the announced nuclear test by the Democratic People's Republic of Korea on the 6th of January 2016 last year. So let's start with the basics. Atmospheric transport modeling is the mathematical simulation of how air pollutants move and disperse in the ambient atmosphere. And with air pollutants, that can be gases, liquids, or solid particles, aerosols. And the examples or the applications where we are interested in is mainly verifying compliance with the Comprehensive Nuclear Test Ban Treaty, or the CTBT. And my colleague Johan Kamps has talked about that in the previous lunch talk, which you might have attended. And actually the most part of my PhD is dealing with the CTBT. And two examples later in the presentation will also deal with that. We can also use atmospheric transport models in the case of emergency response, when there is a nuclear incident or accident at the nuclear reactor. And here you see the example of a nuclear power plant in Norway, where there was an incident, I think, at the end of last year. Atmospheric transport models can also be used for source term reconstruction, and there was some attention in the media by the recent iodine detections in Europe, which comes from ISRN, the map, and we could use atmospheric transport models to backtrack and reconstruct the source. So that is something that we will look to into the future. And then finally, I haven't read the new strategic plan of the SCK-CEN, but in case they are interested in modeling volcanic ash releases, we could also use atmospheric transport models for that. Now, these atmospheric transport models, they require meteorological data. And for the near range, we could use some constant wind factor, some constant wind field, which is depicted here. Here you can see roughly the region of Antwerp. And when we go to long-range modeling, typically we use data from numerical weather prediction models. You can see an example here on the right. Because you see that the wind factor is changing quite a lot with space. So these numerical weather prediction models are used, and they contain information about the wind fields, obviously, but also about temperature and humidity, which can be important for convective processes. Now, these data, as you probably know, contain errors, and they are difficult to quantify. And actually, the uncertainty on these numerical weather prediction models are the main source of uncertainty on the atmospheric transport model output. So if we can quantify the uncertainty of the weather data, we can also quantify the uncertainty on the atmospheric transport models. So the aim of this research, or of this PhD, is to use the ensemble method to quantify the errors on the atmospheric transport models. So now I will try to explain the ensemble method, and for that I will use some new slides to explain it, because in the past I've tried it a couple of times, but with limited success. So I use now this maze to represent the state of the atmosphere. And basically, for numerical weather prediction, you will divide your atmosphere in a couple of cubes, grid boxes, and you calculate the pressure, the temperature, the wind speed, and the humidity for each grid box. So you end up with a high-dimensional phase space, and let's assume that this maze represents the phase space of the atmosphere. You can see a couple of empty spaces which are inaccessible in the maze, and that is also the case for the atmosphere. For instance, if we have a temperature of 30 degrees in one grid box, we cannot have a temperature of minus 20 in an adjacent grid box. So certain combinations of temperature and pressure and wind fields are unphysical, so they cannot be reached. Now then, the problem of solving or the problem of weather forecasting can then be translated in forecasting how you move through the maze. And for instance, we have a starting position here, which is the current state of the atmosphere, which is the current weather. And we try to forecast the state of the atmosphere, the weather, for a time in future. Now, before you try to find the correct solution, we don't know the finish beforehand, obviously. Otherwise, why would we do weather forecasting if we know already the state of the atmosphere in the future? So we should try to walk through the maze without knowing the finish. And actually, we don't know the start either. We don't know the correct initial state of the atmosphere. We can only estimate it. So in reality, we have the following problem. We have again our maze, but without a start and without a finish. Now we try to estimate the initial state of the atmosphere, and for that we use, I think, about a couple of tens of millions of observations every day, but still we don't have an exact we don't know the exact initial state of the atmosphere. Now let's say that the initial state of the atmosphere is located over there, and then we can use numerical weather prediction models, and we can integrate the partial differential equations, and we simulate that the trajectory of the atmosphere will be the following. So after a few days, the weather will be, or the state of the atmosphere will be like this. Now for the same price, or an equivalent possibility would be that the state of the atmosphere, the initial state, is located over there. And if we now apply the same methods, we end up in a different location of the maze. It could be even more dramatic. If the true initial state of the atmosphere would be located over there, we get a totally different path in the maze. So somehow we need to take into account this initial state uncertainty. Because if we know the initial state uncertainty, we might also know the uncertainty on our actual forecast after a couple of days. And that is why we use ensemble modeling to get this initial state uncertainty in a natural way. So basically, we as I said, we can only estimate the atmosphere's initial state, and therefore weather data contains inherently a form of uncertainty. And we can use this ensemble method, which consists of drawing many possible initial states. And for each initial state, we perform the integrations, and we end up with different equivalent results. With equivalent, I mean equally likely. And then the spread between these individual results represents the uncertainty. That's the idea of ensemble modeling. And in the example here, we have used only 3 realizations, but in practice we work with an ensemble of, say, 20 or 50 different paths. So each realization or member is equally likely to occur, as I said, but of course the drawback is that the computing time increases dramatically. For instance, now we work with 51 members, which means that the computation time increases with a factor of 51. Okay, I hope the ensemble method is a bit clear. I look forward to the feedback during the lunch. So now we will look to some 2 cases. And we'll start with the forward problem, where we have a known source, and we try to model the concentration. And for this study, we look at the capability to model the background of CTBT-relevant xenon isotopes in Europe. So remember, the CTBT is the Comprehensive Nuclear Test Ban Treaty. And the treaty is verified by the International Monitoring System, or at least will be verified because it has not yet entered into force. The International Monitoring System will monitor seismic waves, infrasound waves, and hydroacoustic waves to detect nuclear explosions. And besides that, it will also monitor certain radionuclides. And of these radionuclides, also noble gases are monitored, that is specific xenon isotopes. You can see here the map, so it is covered globally. But for this research, we focus specifically on certain xenon isotopes, which we can call conveniently radioxenon. The elements are given there. And the advantage is that the half-life of these isotopes correspond roughly with the time scale of the synoptic scale weather structures. That means that it has a half-life of a couple of days, so it can be transported conveniently by the wind. But the half-life is not too long to avoid accumulation in the atmosphere. Furthermore, there are no chemical reactions and there is no deposition, which is both convenient for the simulations and also from an observation point of view. Now, so actually, if we measure these xenon isotopes at the station, it could indicate that that a nuclear explosion has happened. But we measure all the time a lot of this radioxenon at many places globally, because there is a significant release from civil sources. And these civil sources are tabled here. So a 1 kiloton nuclear explosion which occurs in the atmosphere could have a release of 10 to the power 16 becquerel. An underground nuclear explosion could have a release between 0 and 10 to the power 15 becquerel. But two important civil sources also emit this radioxenon, and this can be detected by the network. And these are the medical isotope production facilities and nuclear power plants. You can see that their release is many order of magnitude smaller, but if they are present or very nearby a station, they can still dominate the measured concentrations at the station. So despite the difference in order of magnitude, they are still relevant and they can be measured by the IMS, the monitoring system. So in this research, we would like to simulate the radioactive xenon isotopes in Europe. And you can see part of the setup here on the figure on the right. We have the IRE in Fleury in Belgium, which is known to be the main emitter of radioxenon for the region. And we have used a 15-minute database, emission database for that. And we are in a unique position of having this database available for research. Besides that, we take into account the nuclear power plants in the neighborhood, and we have estimates of their release. And we have one station at Schaunsland near Freiberg in Germany, where we can use data to validate our model. So we want to assess our capability to model this radioxenon background, but more importantly, we would like to use this ensemble technique to quantify the uncertainty of our atmospheric transport and dispersion model. So basically, we compare our calculated concentration with our observed concentration, but we also compare our calculated spread or calculated uncertainty with the error that we make with the difference between our calculation and our simulation. Here you can see results for the year 2014. There is a gap between October and part of November because of that there was no data available for that period, no observations. You can see the radioxenon activity concentration for different sources. So in the top, you can see the contribution from IRE. And then the second part gives the contribution of the nuclear power plants. CNL is another medical isotope production facility like ERE, but it is located in Canada. And at the bottom, you can see the total of the above sources. The black dots show the observations. The red plus signs show the minimum detectable concentration. And then the blue dots with the uncertainty range shows the forecasted concentrations. And the short conclusions are given on the right. So IRE is the dominant source for the station. But the contributions from nuclear power plants can well be above the minimum detectable concentration, and they should be included. It was such that in the past, the contribution from nuclear power plants was rather neglected, because the total impact on a yearly basis was rather negligible for nuclear power plants. But we see with these results that on a daily basis, concentrations from nuclear power plants can exceed this minimum detectable concentration, and it is important to take them into account. For CNL, we see a limited contribution, but they should be included to get the statistics correct. And on the bottom, you see that overall there is a fair agreement between the observations and the simulations. Now we are trying to repeat these simulations with better data from the nuclear power plants, because I haven't mentioned it, but we use a constant source term for these nuclear power plants, and this is not corresponding with the truth, of course. So we would like to have better emission data, but we experience that it is quite tough to get good emission data from the nuclear power plants. Here are some scores shown, specifically the Breyer score, which is a probability, a root mean square error in probability space. And this shows the capability to model the exceedance of a certain threshold, and the threshold is given on the x-axis. The best results are for the lowest Breyer score, and we see that the ensemble shown in red systematically has a lower Breyer score compared to the deterministic simulation, which is called CF, which stands for control forecast. And this difference between the ensemble and the deterministic simulation is significant, as shown by the right part of the figure. And here the uncertainty bars show the statistical sampling uncertainty based on the bootstrap method. So this difference is significant at the 2 sigma level. It's actually in metrology, it's a well-known fact that the ensemble performs better than the deterministic simulation. And here we show that for at least for the Breyer score, this is also the case for atmospheric transport simulations. Now, with respect to the spread, for that, we can use these so-called rank histograms to validate our spread forecast. And the idea is the following: for every event, for every concentration that we have measured, we rank the simulated concentrations from the ensemble from low to high. And then the position of each observation is compared with the ranked ensemble, and that position is binned. So all the observations that are below all values of the simulated concentration from the ensembles, they are put in the most left bar. If the observation is below all members of the ensemble but one member, then we put it in the second left bar, etc. And in the best case, our rank histogram is flat, which denotes that our observation is equally likely to fall in between all our members of our ensemble. So this is a way to validate the ensemble spread, and we see that it is not flat because there are quite some outliers, so the observations fall outside the range of the ensemble. I think it's about roughly 50% of the observations that we can explain with our ensemble, but about 50% of the observations fall outside. So we still have room for improvement, and we hope to obtain this improvement by using better emission data from the nuclear power plants. As a last application, I show results for the announced nuclear test by the Democratic People's Republic of Korea for the 6th of January last year. And here we don't know the source, but we start from observations to reconstruct a source by backtracking our observations. So we backtrack CTBT relevant xenon isotopes to determine the origin. In this table, I summarized the observations, or the suspicious observations that were made by a station in Japan called RN38. So there were 5 observations of elevated radioxenon concentration, and then also later there was a detection at a station in the United States, at least in the Pacific Ocean. So these concentrations, they could come from civil sources, or they could come from a release from a delayed release from the test site at the DPRK. We don't know that a priori, but we try to investigate with these air transport models whether we can link these observations with a release from the DPRK. From seismic waves, we know that the event took place at the nuclear test site of the DPRK, where also the previous announced nuclear tests occurred. So the idea is that every observation is backtracked by our model to find possible source regions. And you can see in this example here we backtrack one observation, and the results show that the source could either be nearby and weak, or it could be far away and strong. So there is quite some ambiguity. And with one observation we can't pinpoint a source location. So the trick is now to combine information from different observations, and that means both detections and non-detections, to remove this ambiguity. The method for doing that is the following. We assume that a single point source is responsible for the observed xenon, and then we have an optimization problem. So for every grid box, for every grid point, we calculate the source term that fits best with all the observations. So we try to find a queue where we find the best match with the observations, and the SRS fields are what is obtained by the atmospheric transport model. And then finally we want to quantify the deviation between the calculated and the observed concentration via a so-called cost function, and here we have defined the quadratic cost function where we sum the deviations between observations and calculations, the squared sum. With that we can obtain maps with the cost function for every grid box, and an example is given here. Here we have validated our method with fictitious sources. We have used 50 fictitious sources for 3 stations, and we can use for this validation, we can use perfect observations, perfect meteorological data, and perfect atmospheric transport models. So we assume a release at the DPRK, which is given here, and our method gives the following output, the following cost function. So we see that most of the area, most of the domain is of course not likely to be a source. However, there is a narrow plume here, a narrow trajectory where it could well be that the source is located. And we know that the true location of the source is over here, and it fits quite nice with the minimum value of the cost function. When we look at the source term at that location, we find a quite good match between the true source and the calculated source. The true source is given here by the blue line, while the calculated source is given by the black line. And we can see that there is a quite good agreement, or a very good agreement, between the calculated and the true source. Now we apply this method to real data. And in the top you can see the data where we assume that the maximum releases are about 10 to the power 12 becquerel per hour. And this corresponds with releases from civil sources and from an underground nuclear explosion with a limited release. And we see that the cost function values are quite large. So from this we find that it is rather unlikely that the source was below this 10 to the power 12 becquerels per hour. If we assume a larger maximum allowed source term, we allow just the same sources as above, but in addition we allow also releases from an underground nuclear explosion with a significant xenon release. And based on the difference, we can see that that we need this high source term to explain the observation. So this points out that probably the release was quite high, was significant, and since we cannot explain this by a civil release, it might well be from the DPRK. Yeah, we are still in the phase of finalizing the research, so I'm very careful in formulating the result. We have used 50 observations from 3 stations, 3 IMS stations. Now, finally, I would like to show the added value of the ensemble. On the figure on the left, you can see the results for the deterministic simulation. And the idea here is that we define a cost function threshold, and we show the region where the values of the cost function are below that threshold. And the deterministic simulation gives the area where a source is for 100%, where it is 100% likely to be compatible with the observations, and the white area shows where the grid boxes are for 100% sure not a source compatible with the observations. Of course, that is quite confident, and in reality there is uncertainty. So we would like to have probabilistic maps which we can obtain by using the ensemble modeling technique. And here now on the bottom figure we plot the percentage of members exceeding a chosen threshold. And we define again 3 areas instead of 2 now. We have the dark orange area, which are grid points that are for 95%, at least 95% of the ensemble members give that these areas are likely sources, or sources that are compatible with the observations. And the white area are areas where 95% of the ensemble members show that that area is not a likely source and is not compatible with the observations. And now, in opposition with the deterministic simulation, we now have a yellow area where chances are between 5 and 95%, and basically we cannot say much about that area, so I call it a gray zone, although it's yellow in this figure. We have used 51 members to get the meteorological uncertainty. Okay, now I come to conclusions. So atmospheric transport modeling is a valuable tool for a wide range of applications. And for this research, it's used to support the verification regime of the CTBT. It helps to determine the radioxenon background from civil sources, which is the so-called forward problem. And it allows to backtrack radioxenon to possible source regions and estimate the source term, the so-called inverse problem. Radioxenon emissions from nuclear power plants have a significant impact on the IMS noble gas detection network, which is a conclusion that was prior in disagreement with what was previously assumed. And the ensemble is allowed to quantify the uncertainty of atmospheric transport modeling, both for the forward and the inverse problem. Thank you for your attention.